Hello, everybody. My name is Simoncini. I am a lecturer in the Systems Engineering program, and today it's with great pleasure that I am introducing our guest speaker, Alfred Wong. So I know that Al prepared a slide with all his information and research interests, so I will try to be very brief here, say a few things. Al's talk is on System of Systems Engineering in the US Army. He will provide an introduction to the military system of systems and the various ways the US Army conducts a system of systems engineering. Al is an accomplished systems engineer in the US Department of Defense, where he has served in various roles, leading system of systems engineering effort for the US Army. Previously, he worked as a software developer, developing applications for the Army and the Federal Emergency Management Agency. He graduated from Rutgers University with a Bachelor in Computer Science and is a fellow alumnus of our Cornell Systems Engineering program. He is also a Harvard Senior Executive Fellow alumnus and is currently studying in the US Army War College, concentrating on a Master of Strategic Studies. Now, on a personal note, I would like to add that Al was my student when he was in the Systems Engineering program. He picked one of my projects as his capstone project, and in that capacity, he led a very diverse team of architects, civil engineers, system students, of course, regional planners, designers, information science students, and believe it or not, art students in the mix. So the team was tasked by the city of Ithaca to redesign the 3 garage system in Ithaca downtown, and they delivered. They delivered an incredible optimization, wayfinding system for the Seneca garage. And I have to say, I just delivered him the news that it's thanks to him that actually the city of Ithaca implemented that design. So we can say that Alfred Wong left a mark in the city of Ithaca. You can go to the Seneca garage and admire the design, which is a mix of art and systems engineering. So without further ado, Alfred Wong.
Thank you very much, Siri, for the generous introduction. It's actually an amazing honor to be back here at Cornell. It was an amazing experience here as a student. And I'm coming back to talk about personal passion of mine, systems engineering. So, a brief overview of myself. Siri provided a good overview. I've actually, in terms of education, had an amazing experience here as a systems engineer. I participated in Harvard Senior Executive Fellows. Right now I'm studying at the US Army College. I'm not military, I'm a DoD civilian, but most of my classmates are actually all military. Fun picture over there. This is actually a picture at the US Army War College. The general commander of the US Army Pacific was actually giving us a good overview of some of the threats in the Indo-Pacific. And then here I am with the faculty chair at the Harvard Senior Executive Fellows. Fun fact, undergraduates in Harvard, I never knew this before, but apparently they get sorted into houses. I don't know if folks knew that, but it's exactly like Harry Potter, right? Mm-hmm. This is actually one of their house common rooms. It looks exactly like a Gryffindor common room. Like iron, dragon, Candelabra and all the giant fireplace, everything. So absolutely amazing experience. In terms of my career, I used to do software development, software engineering for both the Army and FEMA, Federal Emergency Management Agency. And then eventually, as I moved on to roles of more responsibility, I was a chief architect within the Army's Office of the Chief Systems Engineer. And then eventually I became a director of integration, working on integrating various chemical, biological, radiological, nuclear defense systems for the Army. It's been an amazing career. I've seen a lot of systems in the Army. Couple of caveats. I'll also add, I'll share what I can. A lot of the work I do is either classified or controlled unclassified information. But if you have any questions, I would definitely encourage asking them, I'll be as transparent as I can, but I can't go into certain details, right? Because some of that stuff might be a little bit on a higher sensitivity levels. So, Army portfolio. The Army has a lot of systems, right? If you think about your vision of the Army, it's a very, very diverse set of systems, right? We have platforms up there, the Joint Light Tactical Vehicle, we have artillery, M777s, tanks, and then we have aircraft too, right? We also have a lot of SATCOM, satellite communications, right? So the Army is very much involved in space, right? Invested in space capabilities. We also have long-range fires capabilities. And I hinted at this before, chem bio, all right? A lot of folks forget that there's a huge chemical, biological, radiological, mostly chemical, biological threats out there, all right? And then when we get into smaller scope systems, Army has tons of radios, tons and tons of radios, right? We also have, what you're seeing here is soldier using a network EUD. So we have smartphones, actually. Our soldiers wear a smartphone right here, and then they use it to communicate their location or text message, send text message and whatnot. We also have lots of command and control systems, all right? So if you imagine thousands of soldiers, how are they going to coordinate? How are they going to do logistics? How are they going to send information to each other? A lot of this stuff is very much through our command and control systems. Most of my career experience has actually been in the lower half here and a little bit on the vehicle side, right? I've done a lot of work in command and control systems and designing tactical networks, let's just say. So just a quick overview of where the Army is modernizing, right? We have 8 priority areas. You can kind of see there long-range precision fires, so precision strike missiles. We're also looking at the next generation combat vehicle, right? So think robotic vehicles with guns, right? Because that's exactly what you see there, right? Future vertical lift, unmanned aircraft systems, network. A huge part of Army's modernization is modernizing network capabilities so that we can actually communicate with each other across vast distances too. A shared position navigation timing. An element of modernization that a lot of folks don't necessarily see on GPS, right? Global positioning system. The Army relies heavily on GPS, right? Where am I? Where are my soldiers going, et cetera, et cetera. That over there is a shared PNT device. And then air defense, this is a maneuver short-range air defense vehicle, all right? So that we can successfully defend against incoming missiles, incoming UAVs. And then there's a lot of the more advanced stuff, right? This is the Integrated Visual Augmentation System, IVAS. Army's modernizing with augmented reality, all right? To provide basically, I hate to say this, but I'll say it anyways. Call of Duty-like overlay, right, on the soldier's vision, And then we're also trying to use, at the same time, we're trying to use virtual reality, modernize how we're training our soldiers. You could kind of see here, I'm going to talk about systems, but every single one of these elements have to integrate into a much, much larger system of systems. So a lot of the systems engineering activities that happen in the Army, yeah, they're focused on an individual system like IVAS here, right? But what's the network IVAS is going to ride on? How is this soldier going to communicate with command posts, et cetera, right? So each one of these modernization areas implicitly has a huge system element into it. Each one of these has to integrate and work with a system of systems. So, this is kind of a system-centric view, right? Systems engineering just within the Army is actually very, very complicated. We just look at a radio, just a radio system, they have to worry about antenna. They have to worry about what kind of hardware they're going to be using to process, right? Battery life, that's a huge one, right? Because when your soldier's out on the field, you might have limited charging capabilities. How do you configure your battery? How do you configure your radio? We have something called software-defined radios, where they'll load different waveforms onto the same radio system. And then finally, this is a secure key loader. How do you ensure security of your waveforms, right? You have to load in security keys, so that soldiers can securely communicate with one another. All of that stuff, a single system engineer has to, or a set of systems engineer have to worry about, right? Then you have to worry about outside dependencies. GPS, your radio systems, they rely on timing for GPS, to synchronize with one another. Jamming, all right? A big part is building radio systems that are resilient to jamming. And then you have to worry about training. How are you going to train the soldiers, right? Again, a single system, using a radio example, systems engineers have to concern themselves with all of these elements. And then the final piece, the system-centric view, you have to worry about integrating into other systems, right? This is when you start to see some of those systems. But from a radio-centric view, you're worried about all these things, right? Your radio might have to go into a joint light tactical vehicle, a tank, or a variation of your radio might have to go into an aircraft, right? You have to think about the physical form factor to design to all of these, including your antennas too, right? How do you position your antennas so that they don't interfere with each other? That's very much all the areas that a single system has to worry about, right? And then again, other areas, other attributes and abilities that a systems engineer has to worry about. This is kind of a handful of them. I would definitely point to these last few on the right? Supply chain, all right? How are you going to manufacture your system? In the Army, we have to actually ensure we have secure supply chains, right? US-made supply chains, because if we are going to, let's say one day going to war or battle with another country, our supply chains might not be so secure, right? Cybersecurity, we have to design systems that can sit on classified networks. Those are extra requirements, suddenly, right, that you're placing on top of your systems. Survivability, some systems have to be designed, when we talk about radios, for example, they have to be designed to withstand radiation, right? Because again, our systems might have nuclear survivability requirements, right? And then disposal, right? Environmental Protection Agency, EPA regulations, how are we going to dispose of our systems? And this is kind of an overview of the systems engineering lifecycle that we follow in the DoD. This is actually from the 2022 DoD Systems Engineering Guidebook, right? You guys might have seen some of this in, I think, Dr. Schneider's class, 5100. He hints at, I remember one slide showing the systems engineering beat, right? I'm going to walk through every single one of these processes from a system of systems perspective, but just a quick overview. You have concept development, you have requirements, analysis, and proposition. Then you're designing your system, you're prototyping it, then you're testing and validating it, and finally you're delivering it to the warfighter, right? Each one of these, from a single systems perspective, very, very complicated, right? Especially when you stack all those other requirements up. But then when you look at it from a system lens, it increases in complexity, right? And on top of that, as you're doing your systems engineering activities, there's the Army or the DoD acquisition process, right? The reason why I bring this up is because there's different ways you're going to engineer your system, all right? And that all falls within Army or DoD policy for acquisitions. So for example, if you have requirements already and there's already a solution, you might go to this acquisition framework, all right? If you have something like the integrated visual augmentation system where you think you can rapidly militarize it and then field it to a soldier, you might use this acquisition system. This, the major capability acquisition, this is actually a more traditional acquisition line, all right, or acquisition process, where you're looking at the technology, you're maturing the technology. A lot of the systems engineering activities happen here, engineering and manufacturing development. That's when you're actually, you have validated requirements here, and then you're actually designing the solution, right? And then milestone C is I have a design solution, I can manufacture it, and then here's the gate for an acquisition executive to sign off on that I can actually start producing and delivering the solution. And then software, right? We have the software acquisition process. This is designed around the agile process, basically, right? You have relatively short sprints, and the idea is to continuously iterate and evolve the software over time. This will be important later as we talk about systems, but I just wanted to kind of center you guys on the different ways we acquire systems, all right, and how it impacts the systems engineering process and the systems engineering lifecycle. Any questions so far? Go ahead.
You mentioned that I guess traceability within the supply chain is a critical aspect of procuring things. Have you guys, has there been an exploration of like a shared ledger or something for the supply chain?
What do you mean by a shared ledger?
For example, like you have a closed circuit of like 3 suppliers, so and you have components moving between each supplier before it ends up at the final customer.
Yeah.
When you have like a shared ledger, for example, you can see like added verification that, okay, this component was like this value added process was done on this component.
Yep.
We received it, and this is like a double sign that we like, you know, it's within our location or whatever, and we can confirm that this was done according to this service agreement, stuff like that, which without that shared ledger is just like a US Army has to check each and everything themselves, and they don't have any added verification from.
So here's the beauty of the US Army, right? We let defense contractors do that, right? I mean, I know it sounds like once over, but I'm not familiar if shared ledgers are scrutinized, right, in terms of the supply chain, but there are requirements when we're drafting requirements for the original equipment manufacturers that they have to ensure that their supply chain is coming from US sources, et cetera, et cetera. I know that is a massively big deal when we're manufacturing like tanks, right? Tanks, I like to think of the analogy, the automotive supply chain, right? So all the stuff that goes into tanks, the original equipment manufacturer, they'll be the prime, what we call the prime contractor, right? But then they'll have a lot of subcontractors, similar to the automotive supply chain, where they're providing some level of supply that gets manufactured, et cetera, et cetera. So admittedly, that's an area I'm not super familiar with, but it's again, a lot of times we let the contractor, the defense contractor, manage that and ensure that their own processes are up to speed as they're reporting up to the program manager.
Just a quick follow-up.
Yeah, go ahead.
Would you say like that's like the traceability aspect of it is mostly a solved problem, or is there still space or like
Mostly solved?
is it mostly like a solved problem, the traceability aspect, or
Not at all. Okay, this is I'll give you an example in the DoD. Okay, Log4j. Did you guys hear about the Log4j zero-day vulnerability that happened like a couple of years ago? Not at all, right? So it was a big deal in the DoD, huge deal. Okay, Log4j, software developers out there, we use that for everything, right? Server software uses it, et cetera, et cetera. When the zero-day vulnerability came out, we actually didn't have what we call a bill of materials for our software. On the hardware side, we have a bill of materials, all the stuff that goes into it, right? Who's supplying it, et cetera, et cetera. That might be more like that ledger that you're talking about. But on the software side, when the zero-day vulnerability came out, we didn't know what software necessarily was exposed to that zero-day vulnerability, right? Suddenly, everybody in the DoD was trying to update their Log4j, right? But they didn't know, we have a lot of software in Army, right? We didn't necessarily know what to update, right? And whatnot. There's a lot more scrutiny now. There's policy being developed in place, what we call an SBOM, a software bill of materials. And that's actually, there's discussions right now on extending that even further. So if you think about like nowadays AI, right, is a big deal, right? What are you training your AI on though, right? So it goes even further for a data bill of materials. You know, what data are you using to develop your systems, right? Your software systems. And then even further, I'm hearing early discussion on an AI bill of materials. What AIs are you using as part of this bigger solution, right? So there's early policy on that, all right? But the software bill of materials is a big one that we're seeing in the DoD, kind of trickle down from DoD to the program offices. So hopefully that kind of answers a little bit your question. We need more traceability. Bottom line up front, we need much more traceability.
Final quick question, because
Yeah.
it's related to my work. So would you say like comparatively software traceability is a more critical problem than hardware traceability? Or is it not possible to compare?
I would say both are important, right? I would say hardware traceability is, when we're talking tanks, right, like capabilities, that's more important. And here's the reason why. When we talk about, defense industrial base, right, it's very, very hard to build a defense industrial base, right? Supply chain, hardware supply chains is very, very hard to build up from scratch, right? Software, yes, that's important, but the Log4j piece, if we can update that, right, that's much quicker to fix versus supply chain, hardware supply chain vulnerabilities, that's a lot harder to fix. Does that make sense? I think you had a question?
Yeah, so do these various acquisition practices, do they all have the same uniform OPSEC measures, or do they all have their own set of measures?
All have their own set of measures. Yeah, I'll actually go into that in a little bit, but these documents, right, milestone B will have, like, for example, key performance parameters and key system attributes. It's completely different because you saw in the portfolio, you have completely different systems. Now, there's some measures that we have consistent, okay? Survivability is a big one. And what we call a net ready KPP is making sure that the system can, I think I'm getting at your question, correct me if I'm not, but the net ready KPP is common in that you always have a requirement to operate on certain classified networks. It's kind of a blanket like, hey, did you satisfy your net ready KPP? Now, when you do your requirements decomposition, that goes into that next level. Are you required to operate on top secret networks or secret networks or unclassified, right? Because it completely changes your detailed requirements, right? Your performance specifications. But at the top level, that blanket net ready KPP just covers like kind of all. Does that make sense? Okay. Any other questions, comments? Okay. So what is a system? I'm sure everybody in here knows what a system is. I like to do this because a lot of times when I'm speaking to general officers or even other engineers, right? Systems means different things to different folks, right? If you can kind of see all the different, this is just a handful that I pulled, right? From the CBOC, right? Systems Engineering Body of Knowledge, Defense Acquisition University. I love NIST because they made it like the most complicated definition, right? National Institute of Standards and Technology. I tend to like this one. This is the DoD Systems Engineering Guidebook. But bottom line up front is when I speak to folks who aren't necessarily engineers, and they ask me what system is, I like to keep this definition. It's a set of systems that share the same use case, all right? That's it, nice and simple, right? Because most folks will understand a use case, and and this is top level, right? So when they see what's, a set of systems that all go into the same use case, oh, I get it, easy enough, right? This is important, and the reason why I emphasize the use case, you'll see later, those use cases are critical to tie systems together. So this is kind of the lowest example of systems I usually provide an overview on, right? If you think about a vehicle, this is its own system. This is a joint light tactical vehicle. You'll have a program office, what you saw in the previous acquisitions, right? A program office executing and designing a JLTV. Then you might have different program offices designing different radios, okay? Or they might be designing different mission command systems, mounted mission command as an example, right? All of these are happening independently, right? But when they integrate together, they have to, all of those radio systems have to go into a vehicle, right? So they all have to integrate together. That vehicle, to me, with all the radio systems, the antennas, everything, and this is a GPS. I talked about Assured PNT. That's another system that gets designed on its own, gets procured, designed on its own, right? They all have to go into the same vehicle. They have to support the same set of soldiers, right? So if you think about a system of systems, Again, I like to think of a vehicle as kind of that lowest level of systems in the Army. I'll go into much higher levels in a second, but vehicle is easiest for folks to visualize, right? We have similar designs for dismount. So if you think about a soldier, he's got his backpack, he's got all the gear he's got to carry. He's also got radios, right? He has his own smartphone, right? The network UV and whatnot. He's got his rifle, et cetera, et cetera. So system of systems, again, even at the soldier level, you have system of systems, right? And then there's frameworks around designing a lot of those systems. And then when you're putting all this stuff together, I like to talk about swap C, right? Size, can you physically fit all these systems together? Because a lot of these systems are being designed independently, all right? So they might be conversing with one another, right? But they have to worry about, can they fit in that vehicle? Weight, how much is additional payload is that going to add to the vehicle capacity? Power, this is a big one, okay? We actually have some vehicles where they're having issues providing enough power for all these computing systems and radios that we're putting on the vehicle. Again, at the system level, you have to consider, an engineer has to consider this. Cost, the Army problem is a problem of scale. We have a lot of soldiers, right? It's very, very different than the Air Force, right? And the Air Force has a handful of F-35, super complicated systems, but they're far fewer, right? Cost is a big one that we look at because we have to field a system to almost every single soldier. And then finally, cooling. That's again another big consideration up there with power. Are you generating too much heat with your systems? So, what do more complex system of systems look like, right? So here you might have two squads of soldiers, right? They have their own radio network. We already talked about how the soldiers have their own system of systems themselves, right? But then they have to talk onto their mechanized infantry, so they have to deploy onto vehicles, right? They have to be able to communicate with those vehicles, share information with those vehicles. They also have SATCOM, right? So they have not only tactical radio networks, they have SATCOM, and they have, their own smartphones and the mounted mission command computers on the vehicles, right? Not only that, they have to talk laterally, right? So they have to talk to tanks that might be operating in the same vicinity as the mechanized infantry. They also have to talk to a command post, right? So all of a sudden, when you're designing systems, you have to consider a lot of these additional elements, right? The command post itself comes with a ton of different communications equipment, right? And then at the next level, you have different types of command posts, okay? So you have brigade engineering battalions, brigade support battalions, so on and so forth. Again, each of these command posts might have a different specialty. Some of them might be worried about logistics. Some of them might be worried about intel, et cetera, et cetera. So you might have non-organic systems, right? So if you think about it, where's your SATCOM going to, right? A lot of times you have to communicate SATCOM to a network operations center, all right? They might be in continental US or they might be in a foreign country somewhere. We have teleport sites. This is basically where satellite touches the internet, right? They might have to talk to assets that are in the DoD information network and all these other assets that might be supporting those. So if you think about an Army fire chain, right? So I don't know if you guys have seen the movie, but like you'll have a forward observer, right? He goes, I need guns on that target over there, right? And then an aircraft or a helicopter might come flying in minutes later to attack a target, right? All of that stuff happens along a very, very complicated fire chain, all right? That goes all across, all right? But this is kind of a good overview of how complex some system of systems can get, especially in the Army, right? Any questions, comments before I go on? Go ahead.
So you're saying like in the Army there's different teams of systems engineers working on different components of one large system?
There's different groups, different units, I should say, different units that have very, very different systems that they're using, not working on, but they're using for their mission, right? So you might have, for example, reconnaissance might be flying a bunch of UAVs or helicopters or whatever, right? Not helicopters, but UAVs mostly, Or reconnaissance might be using satellites for imagery, right? That's a completely different unit than soldiers that might be on the ground providing area security, right? In the Army, we have a lot of different types of units. And if you think about the different types of systems that they might employ, they actually very much vary, okay? In terms of the software they're using, in terms of the radio networks they're using. Like, for example, logistics is huge in the Army, right? You can imagine how the amount of effort it takes to bring food, rations, supplies, ammo, all that stuff in, right? They use a completely different satellite network than a lot of these soldiers do, you know, and that satellite network connected to different cloud systems, et cetera, et cetera. Does that make sense?
Yeah.
Go ahead.
So within the systems like you described in the Army, like I'm guessing a lot of the design comes from like various units, right? That are like discrete units.
Yes and no. I'll actually get into the design in a second. It's not as organized as I would like to be, but hopefully then a couple of slides forward, I'll show you some insight into how we design our system. It's not super elegant. I'll caveat. All right. All right. So if we look at kind of the systems engineering lifecycle, right? What are some early things that what are some earlier system activities that we might do, right? This one, you know, a lot of times before we even know what system we want to build, you have to do a gap analysis, right? You have to identify what capability do the soldiers need, right? So this is mostly subject matter expertise support, right? Because a lot of times you're providing expertise on what we have already, and can we use what we already have to satisfy that gap, all right? So for example, if I needed a better way of communicating this, right, my smartphone to another, because in the Army, it's bring your own network. We don't have cell phone towers or Wi-Fi, right? We have other networks that we can connect to this that perform better, that can meet the requirement. Again, this is mostly subject matter expertise. This is actually where a lot of the fun is, admittedly, right? I call it system opportunities. If industry has an amazing new capability, right, can we use it in the Army, all right? Easy example, I like to return to this. I was part of the early down select for smartphones for the Army, all right? So when we looked at this, right, Army this was like 2010, 11-ish, right? When smartphones were like really getting popular, right, in private industry. But could we use this in the Army? Well, from a system perspective, again, this goes back to bring your own network. We have a network in place, right? It sounds obvious, but at the same time, it's okay. But if you want to use this, where do we have that network in place, right? If you look at that previous slide, you know, does it have the capacity? Because a lot of these radio networks are very low bandwidth networks, right? So if you imagine, I can't use Netflix on this, right? Soldiers aren't using Netflix on this, but can I send position location information in a very short pulse packet, right? Yes, we can, you know. So we're also developing architecture products that describe new capability. This is actually very, very important. This goes back to the use case, right? So what the use case that we, system use case that we use in Army, or that we build in Army, we call them mission threads, okay? So I like to think of a mission thread as a very high level use case, right? Of the activities that a soldier might do to perform a particular mission. What you see here is a broken out, this is a system activity diagram, broken out activity diagram of soldiers actually conducting a immediate decontamination, what we call. So they're literally, it's a wet wipe, okay? When you can see the soldiers, when they're in their mask and their protective gear, they'll take out a wet wipe and then wipe down their equipment that might be contaminated with chemical agents, right? But this fits into a much, much bigger mission threat, okay? This is end-to-end decontamination. You can kind of see this is like much, much longer, right? But then when we think about even bigger, these mission threads were actually used as part of another study. It was end-to-end CBRN. So it goes from, can I sense a chemical agent? Can I put on my mop gear? Can I operate my mission? And then can I decontaminate, right? You can imagine if this is just decontamination, how big that mission thread might be from an end-to-end perspective, right? Because soldiers have to do all of that stuff as they're conducting a mission, you know? So mission threads can get very, very complicated. This was actually being looked at for new decontamination capabilities that soldiers never had before. So again, we would have to decompose the activities that a soldier might do if they had this new capability. That's a lot of the earlier systems activities that we're doing, all right? Next goes into the requirements, right? So going back to that activity diagram, that mission thread, that's very, very important. So when we go into requirements, when we have a new system or new capability need, you know, what are the interfaces that these systems have to interact with, right? Again, cell phone or smartphone radio, right? What are the radios that has to go into? What are the legacy equipment? What is the legacy equipment that the soldiers have, right? Here we're doing a ton of trade space analysis too. So what I'm showing is actually the, should put a label on this, the DoD mission engineering guide process. So the idea is that you have a mission problem, you're developing you're characterizing your mission. So you're developing a scenario, a vignette, but then you're also developing those use cases, okay? From there, you might look at different architectures, do your analysis, and then determine which architecture best satisfies the mission metrics, let's just say, right? So if we look at the CBRN capability that I was showing you on the previous slide, you know, there's trade space. Can I have better sensing? If I have better sensing, I don't need to decontaminate as much, right? Because I'm less exposed to the chemical threat, right? If I have better protection, you know, well, I might have to decontaminate more because that protection might not be so disposable, right? I want to decontaminate it to be able to reuse some of that equipment, et cetera, et cetera. You know, there's trade space. We were looking at trade space for that was actually the last systems activity I did, was looking at trade space between a lot of that stuff, all right? Any questions so far? Awesome. All right. So design, right? Admittedly, this is where I have the most fun in systems. Here, you're actually designing the system architecture, right? Well, when the solution matures a little bit more, you're actually able to see, okay, now that I know that the capability need, if the capability need is for one soldier to communicate to another, and you're designing a smartphone, now I can go, oh, I have a smartphone capability. How does this fit into the system architecture? Here, we're also very much working with interface standards, right? So we have a policy in the DoD, modular open systems approach. But the idea is the military needs to stop building their own proprietary standards, right? They need to use open source standards, right? Historically, we've had a problem using military standards, right? Because of that, we're incompatible with industry solutions because they have to be militarized, all right? So we're trying to shift away to a more open standards approach. And then reference architectures. Reference architectures are a systems engineer's best friend, to be honest, because if you're designing a system to a reference architecture and everybody else is, theoretically, they should be compatible with each other, right? It makes integration easy, right? I'm showing here a PNT from the Department of Homeland Security. I'd love to show the Army one, but that's controlled information. But the idea is the same. If I'm designing GPS, right? There's certain GPS standards. If you're a GPS producer or GPS consumer, right? There's standards already in place for you to design tools, right? If everybody's following those standards, the idea is when you integrate them together at a system level, far easier, right? Here's another example. So if we go back to the vehicle, we actually have a standard called the C4ISR EW Modular Open Suite of Standards, CMOS. We call it CMOS, all right? But this just should provide an overview of if we standardize the way different systems integrate into the vehicle, they'll make things easy when we're integrating the vehicle, right, together, and they'll be compatible, et cetera, all right? So how do we design our systems? Going back to that original slide, right? That with all the networks, all the vehicles and everything. How does the Army design systems? We actually design them using, under the term, capability sets, okay? So capability set architecture is the set of radios, command and control systems, everything, all the network devices, I should say, network or computing devices that go into a particular brigade, let's just say, right? This is kind of a high-level operational view of capability sets, and hopefully this will go into the gentleman's question on how do we design our systems, right? So this is kind of how it happens today, all right? So if you think about a brigade and all the different soldiers, right? We have what we call a table of organization equipment. That is every role in a particular unit, in this case a brigade, right? So you might be a platoon leader, first platoon leader in Alpha Company, blah, 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 right? Every single role in a brigade, what equipment they all have on paper, right? So that all goes into the table of organization equipment. That goes down into the unit level. So if we have a specific unit that we're designing towards, because there's a reference architecture, but then, or a high level, how it's designed to, but then when you actually go to a soldier, an actual unit, it usually differs. But from there, we have what we call bases of issue plans. These are developed independently at the program level, okay? So the requirements, the warfighter representatives within these programs, they'll design the basis of issue plans. Which soldier is getting what equipment, okay? It's not designed so that if you look at the vehicle, it's not all designed together, right? Instead, it's this soldier is getting this radio. He also happens to be getting this equipment and this equipment. All of it falls together on the same soldier. They have to integrate together, okay? And then from there, you combine basically all the bases of issue plans for all the different systems into one product, and you have a capability set reference design. That's kind of how it works in the Army. It's not perfect, admittedly, right? Because sometimes, admittedly, we do have issues where basis of issue for a system might be designed for a system that was dependent on another system, right? And it's not there, right? Because that basis of issue was different. It was distinct. So there's a huge effort in combining these into one design and then double checking the design to make sure that the systems is actually what it should be, all right? Case in point, if I have a basis of issue plan for the smartphone, that same soldier should have a radio to connect to that smartphone. Sometimes that happens, that soldier, we forgot to give him a radio, right? Suddenly he has a smartphone, that's kind of useless, you know? So again, this is kind of how capability sets are designed in the Army. Any questions, comments on that? Hopefully I answered your question over there, so. So now we go into prototyping and development, right? So at the system level, lab and field experimentation, development to testing. That's a lot of the stuff that we do. We also do performance analysis. Because now we have a systems design, right? So now that we have a system architecture, let's just say, we can actually carve out that architecture, put it in a lab, and actually see, does it all work together, okay? What you're seeing kind of is a notional architecture. So we might have a representative command post, a representative vehicle, representative soldier, connecting to other servers, et cetera, and then we might play it out, you know, do a virtual fires mission to see did the system work as intended. So this is just a snapshot of how this might look. But yeah, so this happens a lot, this lab and field experimentation, all right? When we do field experimentation, same thing applies, right? So we might give a handful of soldiers these systems and have them go out into a field to actually do some exercises, okay? A lot of times this is used to test the radios, to be honest, and the network capability, right? So we have a new radio that's radio with a waveform that's untested. We might have them go into an urban area or a wooded area and test it. Is the system working, system of systems working as intended? Because a lot of times, if you think about, admittedly, we might take for granted, right, that we're always connected to a cell phone network. If the connectivity is spotty, right, can you still use Google Maps, et cetera, right? Sometimes, you can't. Same thing with the application, military applications, you have to test it. You can test it virtually, right, in a lab environment, simulate it, emulate it, but it doesn't beat real world testing,
I have a question. So I see that you're involving the users, the soldiers during testing. But are you involving them even before that, before
Yes.
designing, when you create the requirements,
Yes.
after their needs? How do you involve them in the
So,
design?
so the requirements, there's high-level requirements that the soldier drafts, the warfighter rep drafts up, right? The warfighter rep will engage with soldiers to make sure that those requirements are developed to their needs, all right? That's the soldier involvement piece. There is a gap, right, in the admittedly in the acquisitions process where we might not know what the solution looks like, basically between here, right? Because we have to design something. We have to actually create something first. There's not a lot of the design process. I know where you're hinting at. I forgot it. Maybe you can help me out there.
The system design thinking process?
Yeah, like
Human-centered design?
that was
To
it.
try
Yeah,
to
yeah, yeah.
observe,
Yes.
interview,
Yes.
and pretend to be the soldier and come up with needs
Yeah.
that then becomes
We
requirements.
we don't do that very well in the Army, admitted. We're starting to, right? We're starting to implement design thinking. So there's, in some circles, they're starting to create personas that represent different soldiers, and start thinking, oh, how might it look like? It's far easier to just put it in the hands of soldiers, to be honest.
Yeah, so
design it.
to make it and then recuperate that human part with
Yeah.
the testing.
Yeah.
But the problem is that you might develop something that they don't need.
That happens a lot.
Okay.
We get criticized for that in our DoD,
you spend a lot of
Army,
money.
all the time. Yes, right.
Developing
So if
something
I'll give you an example. All right. If I go back to, this process, right? This takes 5+ years. Okay. This takes years. Okay. So by the time I have something put in the hands of soldiers, I might be closer to a year. I might be 3 years down the line, right? So I might have designed something that the soldiers didn't want or they didn't need, right? There's a push more towards a more agile approach, right?
Yeah.
Especially for software. That's why this acquisition process came about, right? But even here, we have what we call soldier touch points. We're frequently putting this stuff in the hands of soldiers. So when I talk about the integrated visual augmentation system, the Microsoft HoloLens for soldiers, right? They're doing rapid prototyping. They have tons of soldier touch points where they have, Microsoft will build a version of the HoloLens and it will go, okay, here's 5 soldiers, let's put them in, have them run an exercise. And then they will get that feedback. It's invaluable, to be quite honest. We need to do that
Save
better.
money and time.
Oh yeah, we need to do that better in the Army. Can it work for a lot of systems? Absolutely, right? Can it be done better? Absolutely. Can absolutely improve on that process. So, okay. What time am I lecturing?
Oh,
Am I over?
no, not
Oh.
yet.
How much time do I have left?
1 minute.
Oh, okay. I'll make this real quick.
But we can.
Verification and validation. We might look at instrumentation. Okay, that's a big piece. We also might look at how we're testing the mission threads. If we go back to those original mission threads, right? A lot of times we have to develop the metrics and execute those mission threads to make sure that they've been designed as is. And then we field, right? So we might do system fielding. When I go back to all those systems that go into a single unit, you can imagine all the schedule coordination that we have to do to deliver a capability to a single unit, right? So this is just a handful of lessons learned in system, right? Biggest ones, to be quite honest, is you at the system level, you have limited decision making to influence all of the systems, right? Because the system is bigger than what you manage, right? Than your portfolio. The requirements often aren't clearly defined, but more importantly, the metrics are very, very hard to design, okay? For example, if I have a fires thread from a soldier looking to fires on target, how do I measure that? Can I measure, and do I measure end-to-end time that it takes? How do I instrument to measure that, right? It's very, very difficult. And this is probably the biggest one. You often don't know the characteristics of a system until later in the system life. And then this is another big one too. Workforce talent, right? I learned everything I did about systems on the job, right? There's no education system, or limited, I should say, education systems that offer system training, let's just say. I heard Cornell has one, a new one, relatively new. So, and then the final piece I'll end with is lessons learned for systems engineers. Soft skills, okay? You guys might be super smart in your technical domains, work on your soft skills, okay? Communication and emotional intelligence. A lot of times as systems engineers, we're translating between different stakeholders, okay? So you might have a user representative who is not technical at all. But then at the systems engineering level, you might have to engage with a chemical engineer, biological engineer, a software engineer. All of them speak different languages, right? So a lot of times, that communication and soft skill is super important. Another thing also is because you're a systems engineer, you might have expertise in some disciplines, right? You're not going to have expertise in every single discipline, right? Build that coalition, all right? Build your network of subject matter experts that you can build on. And this gets to your point. Serious continuous dialogue with the end users is very, very important. With that, I know I'm probably 1 minute over, 2 minutes over. So I'm going to end. I want to leave time for questions, but I'll be here. So if anybody has any questions, hopefully that was insightful and intuitive. Any questions?
Any questions?
Comments? Is it good?
A lot of questions during your talk, so it was very interactive.
Could you say a bit more about agility?
Yes.
That you sort of get surprises of sort of following what's going on in Ukraine, that all of a sudden these little things,
Yes. So
messing up all the systems.
well, so the Ukraine is an interesting case study, right? We study Ukraine way too much in Army War College, to be quite frank. We talk about Ukraine a lot, almost every day. But a lot of times, our agility isn't where we're at in the Army. When I talk about the defense industrial base and the capabilities it takes to bring stuff online, we tend to move very, very slow in terms of adjusting to those capabilities. I'll give you an example. In Ukraine, they're using tons of UAVs, right? Tons of UAVs, and it's actually changing the way they fight, right? Very much so, all right? In the Army, we're trying to adapt that, right? But again, when I go back to the acquisitions process, this takes a long time.
Yeah,
Okay.
no, that was.
Yeah.
At that point, the technology has changed, right?
Yeah, like we have operate urgent capability acquisition. If we know what UAV we're gonna buy, this is the way, right? But to roll it out for the big army, problem of scale, right? We have to have validated requirements, like there's a whole process. It takes at least a couple of years to roll it out as a formal program of record. So our agility isn't where we want to be, but that's changing. We have options now. This is a relatively new process. Previously, all systems had to be acquired under this, which could take 5 years on average. Okay. Now that we have options, this adaptive acquisition framework was rolled out in 2020. So we're starting to see some stuff come out of it, to be honest. Like hypersonics is a big one that we're able to rapidly adopt. There's a couple of other capabilities, but again, agility, Army, they're not synonymous, to be quite frank. Yeah. The most agile forces in the DoD, I would say, is the special forces because they're much smaller, right? And they're willing. A lot of times they're experimenting with a lot of new stuff, and a lot of that stuff, if they prove out to be good capabilities, we adopt them in the Army actually. So we'll benefit from the agility of the special forces. Did that answer your question? Okay. Any other questions, comments? Sweet. All right. Well, that's all I had. Thank you very much. Hopefully that was a good question.
Thank you. That was awesome.